Okay, so welcome back, and today we are going to start chapter 8, and that's going to be on confidence intervals. And so when we talk about confidence intervals, this is where we start to move from the descriptive statistics to the inferential statistics. So up until this point, all the videos have been about, hey, what if we know mu, sigma, the population mean, the population standard deviation, and use that to calculate things like probability of a certain event, like what we've done in chapter 6 and chapter 7. Now, with chapter 8, we still have to keep in mind chapter 7 information, because what we're going to do is we're going to start with calculating confidence intervals for the population mean. Well, why would we want to do a confidence interval to begin with? Well, that's where the inferential statistics part comes in, because the whole idea of statistics is, if you remember from chapter 1, is we use statistics, right? The numbers from our samples, we use sample data with the sample statistics to what? To draw a conclusion about parameters that we want to estimate, that we want to target, right? So let me do let me show you the way I usually try to get the point across as far as with the statistics. And the best way to do it is looking at a bullseye. So if we look at a bullseye, so here's the bullseye right here, okay? And then we have our concentric circles, okay? And so let's say what we're trying to target is the parameter, right? So here's mu. So now remember from chapter 2, from our discussion on statistics, and we talked about the sample mean, right? We talked about different things. And we talked about the sample mean, and we said that, hey, part of this sample statistics is we try to use those to target the mean, the true mean, the population mean. And so we also talked about how there's variation from sample to sample, right? So if I take one sample of size n and I calculate the sample mean, that value probably is not going to equal mu. And if I take another sample of size n and calculate the sample mean for that one, not only is that value not going to be probably equal to mu, but the sample mean of the first sample and the sample mean of the second sample aren't going to equal each other. And we also talked about this in chapter 7, where if we keep doing this process over and over again, where we take a random sample, calculate the sample mean, take another random sample of the same size, calculate the sample mean for that one, and we do that over and over again, we're going to get a whole bunch of values, and eventually we're going to get a distribution, right? And under certain circumstances, we can apply the central limit theorem, and we can have a normal distribution, right? We know that x bar is going to have a normal distribution with a particular mean and a particular standard deviation, sigma divided by the square root of n. And the population, the mean of the mean of x bar, the sample mean, the mean of the mean, will be mu, population mean, okay? But what are we doing here? Well, we're going to use the different x bars. So as we take a sample, right? Sample 1, sample 2, sample 3, sample 99, sample 15, sample 5, let's do sample 1,000. So what do we get? We get numbers all over the place, right? And so the idea is that we know that x bar is used to target the population mean. But it's based on one sample, right? And if we take another sample, we're going to get a different number. If we take another sample, we're going to get a different number. And we're going to get all these numbers But the question is, well, how close are we to the true parameter, right? The parameter. How far away are we? Okay? And so that's where the idea of a confidence interval comes in, is because we're going to use confidence intervals to kind of like be a net, where we're going to capture all of the possible values that we could have for x bar within a certain range. And then based on that net, based on all of those possible values, then we're going to be confident to a certain level that the true mean, mu, is going to be in that range of values somewhere. And the method that's used to kind of create these confidence intervals is a sampling method called the Bootstrap Method for estimation. Okay, and so we're not going to get into what the Bootstrap Method is and how it works, but all you have to do is basically we're going to build our confidence interval around the thing that we're using to estimate the parameter. In this case, we're talking about x bar, okay? So we're going to get to that part in a moment, okay? But the question then becomes, well, why x bar? Well, why are we using x bar to try to target the mu? Why can't I use something else like the median or the mode or the mid-range or some other value? X, I can use some x value, right? Why is x bar? And that brings up another interesting point that we're going to talk about first, and that goes into what I call the anatomy of a confidence interval. So we're going to talk about that in a moment, but this is the idea, is just because I calculate a sample mean doesn't mean, one, that it's equal to the parameter, which most of the time it's not going to be. But also the question is how far am I away? Am I close? Am I far? So it's not good enough just to have a sample mean if I'm going to estimate. I'm going to want a whole range of values that, hey, I'm going to know that it's going to be in this range of values somewhere. Okay? And we're going to use the central limit theorem to help us, because there are certain circumstances, like the law of large numbers, that we're going to use that are going to help us determine what we're going to use. Okay? And so let's get into that in a moment. Okay, so here's our target. Okay? Now, let's talk about the two pieces of a confidence interval. What I call the anatomy of a confidence interval. So, okay. And I abbreviate confidence interval CI, so you'll see me do that from now on. Just realize CI is confidence interval. It's not confidential informant, it's confidence interval. Okay, so anatomy of a confidence interval, the two pieces. Okay, the two pieces that we're going to talk about is the point estimate, right? And the margin of error. Those are the two parts that make up the anatomy of a confidence interval. You need both of those to construct a confidence interval. Okay? So if I wanted a confidence interval, I want to use an estimate. Okay? And in the Bootstrap method, we're going to use our estimate as in place of mu. Right? So if we know, for example, if we know we have a normal distribution, right? Well, if we have a symmetric and bell-shaped distribution, like normal, we know that the mean of the population is here, right? Well, what we're going to do is we're going to replace the mean with our point estimate, and then we're going to go out in both directions by a certain degree, by a certain distance, based on our margin of error. So we're going to go out to, let's say, here and over here, equal distance. So we're going to add our margin of error to get to here, right? And we're going to subtract off our margin of error to come here. And this is the idea that we're going to use to construct our confidence interval. Okay? So now, let's deal with this piece here, the point estimate. Well, what point estimate are we going to use? Well, let's start with the mean, the population mean. So we'll start with that parameter and then we'll move to other parameters as well. But let's start with the mean since that's the easiest one and the more intuitive one that people understand. Okay, so let's say we want the confidence interval for the mean, okay, for the population mean. So let's say we want a 95%. Let's say we want a confidence interval that we're 95% confident that it's going to have the true average of the population, mu. Okay? Let's say we want to be 95% confident. So we want a 95% confidence interval for the population mean, mu. Okay? So what point estimate should we use to target mu, right? Well, we could use, like I said, different point estimates. There's all kinds of different point estimates we could do. You could just pull numbers and use them. So again, just because you use a number to estimate a value doesn't mean it's a good one, okay? So in reality, what we want to do is we don't want to just use any old point estimate. We want to use the good ones, or even better, we want to use the best ones, okay? So what are the characteristics that we want to look for that we'll know that we have a good estimator or a point estimate, okay? Well, the three things that we want is one, we want a point estimate that's unbiased. So what does unbiased mean? Unbiased means that if we take the expected value for the sample statistic, okay, whatever our estimate is. So if we take the expected value of the point estimate, the expected value of the point estimate should be equal to the parameter. So in this case here, we want the expected value of whatever our point estimate is to equal mu. And in that case, it'll be unbiased. So in other words, what we're saying is this. If we take all of the possible samples of the same size and we calculate the statistic for all of those samples, if we take the average of all of those samples and the average equals mu, then it's an unbiased estimator or an unbiased point estimate, okay? So that's one thing. Two is we want a consistent estimator. So what does consistent means? Well, this is where the law of large numbers helps us. Because the law of large numbers tells us that if we take a large enough sample, then, or as sample increases, the value of our estimate gets closer and closer and closer to the parameter. Okay? That's what it means to be consistent. It's, using the law of large numbers. We saw this used in chapter 3 when we talked about probability. And we saw how relative frequency definition, right? The relative frequency of an event gets closer and closer to the theoretical definition, the theoretical probability as sample size increases. So we've seen the law of large numbers work before. It works very similar the same way, and here, it's really, and it's intuitive. It should be intuitive because if I look at a population here, right, and I know mu is in here somewhere, right? Well, if I take a sample, and I take X bar, right? And then I take a larger sample and calculate X bar, and take a larger sample, and a larger sample, and a larger sample. Well, look what's happening to my sample. Eventually, if I take my sample big enough, I'm going to have the entire population. If I take the average of the entire population, it should equal the parameter mu, right? So it makes sense that as my sample gets bigger and bigger, my value of X bar should get closer and closer to mu. That's what consistence means. So as sample size increases, so as n increases, X bar approaches mu. That's what consistent means, okay? So that's the second characteristic. Now the third characteristic is what we call relatively efficient. And what relatively efficient means that if we took all of the estimates that are contenders for being the best, right? We only want the best. We want to use the estimator, the estimate that has the least variation from sample to sample. Okay? So we want the estimate with the least variation. So those are the three things. If an estimator or a point estimate satisfies these three or has these three characteristics, then we would say that's a good estimator. That's one that we want to use. Okay? So now, what are some of the estimators that we know of that do satisfy these? Well, it shouldn't be a surprise that some of the ones that or most of the ones that we've been using so far are. And in fact, X bar is the point estimate that satisfies all three of those as an estimator for mu. Okay? And again, this should, again, from our talks from chapter, chapter 2. For our talk from chapter 2, we learned that the mean, as a measurement of center, has the least variation among all of the measurements of central tendency that we talked about. So it has the least variation. Okay. We also talked about in chapter 7, using the central limit theorem, that how the expected value of X bar equals mu. Okay. So and it makes sense also from our conversation that with the law of large numbers, that as the sample size increases, X bar gets closer and closer to mu. Okay, so it does satisfy all of the three conditions. So X bar is the point estimate that we will use for mu. Okay, now the margin of error. Let's talk about that. Let's start by, again, going back to the big idea. Here's the idea. So let's say I have this distribution, right? And let's say, oh, by the way, we're talking about X bar, right? We're talking mean. If we're going to use X bar as a point estimate, it would be nice to know the distribution of X bar, right? And it would be nice if it was something easy that we could use, that we've used before, right? Well, what if it was normal, right? So what if we have the distribution of X bar being normal? Well, under what conditions is X bar normal? The central limit theorem says that at least 30. So let's assume that for all purposes, let's assume n is at least 30. And by the central limit theorem, X bar is going to be approximately normal with a mean of mu, which we don't know, right? That's the whole purpose of a confidence interval. We're trying to figure out what mu is, right? And a standard deviation of sigma divided by the square root of n. So now we're going to use the idea of the bootstrap method, and we're going to replace the population mean with X bar. And we're going to create an interval by think about it this way. The bootstrap method basically says, what if I use X bar, because I know X bar is my best point estimate, right? So I know that the true mean of the population is mu, right? But I know, based on everything we've talked about, X bar is close. X bar is close to it, somewhere around here, right? We know that X bar tends to be very close to mu, right? It's much closer to mu than X, right, as far as distribution, right? So we know that. So the bootstrap method says, okay, well, why don't we do this? Why don't we just replace mu with X? Okay? Or X bar, rather. And now, let's based on this distribution, let's figure out what the range of values we need to make sure that we capture, let's say, 95% of all of the possible values that we could get for X bar based on the sampling distribution of X bar. Does that make sense? So in other words, we're going to use X bar to cast a net out, and then hopefully by using X bar to cast the net, knowing that X bar is pretty darn close to where mu is, that will also capture mu in the process. So in other words, we're going to use X bar and the distribution of X bar to figure out how far this way and how far this way we need to go. So that way we capture, let's say, 95% of all of the possible values for X bar, right? So what we're going to do is we'll figure out this value, right? So we'll figure out what this value needs to be, right? Let's say X bar 2, whatever that is. And we'll figure out what this value is based on how far we're going out. We'll call that X bar 1. And then what we'll do is, hey, since we're capturing 95% of all of the possible values of X bar, and we can do that, right? There's nothing, I mean, since we know it's normal, that's easy, right? Right? So because let's use the empirical rule, right? If I want to capture 95% of all of the possible values of X bar, right? And I know it has a normal distribution. How many standard deviations should I go out on either side of the mean? 2, right? The empirical rule says that within 2 standard deviations is 95% of all of the values of the population approximately, right? So what if I go out 2 standard deviations this way, and I go out 2 standard deviations this way, right? And so now that's what I'm going to use to figure out my confidence interval. So I'm going to add 2 standard deviations here. I'm going to subtract off 2 standard deviations here, and then whatever that value is, that's going to construct my confidence interval. And so here's the thing. If I construct this confidence interval where 95% of all of the values of x bar are between. So I know, based on the normal distribution, I know that 95% of the values for x bar is going to be between this number and that number. Great. Is it also reasonable to also think, okay, that I can be confident that the true average of the population, mu, will also be in here somewhere? Is that reasonable? Yes. In fact, how reasonable? Well, how about 95% confident that the true value of the mean is in here somewhere? Based on just what we know about x bar as a point estimate, right? It's the best point estimate, so it's got to be close. And as long as we use a large enough sample size, not only are we going to be closer, but we also know that the distribution of x bar is normally distributed, which means we can figure out what the two values need to be. Okay, now, how do we figure out what two standard deviations is? Well, how do we, well, two, okay, what is the standard deviation? Well, what are we talking about? We're talking about the standard deviation of x bar here, right? This is the standard deviation of x bar. So in other words, what are we doing? We're taking 2 times sigma of x bar. So what is this? So let's replace this, right? So this will be negative 2 times sigma over the square root of n, right? And over here, this will be positive 2 times sigma over the square root of n, right? So now, this is the standard deviation, right? Because we're dealing with x bar, the standard deviation of x bar is this. So we're going to do negative 2 times this, so we're going to do two standard deviations this way, and then 2 times sigma divided by the square root will be 2 standard deviations that way. So this is the second part of our confidence interval. So this is the idea, and I hope this makes sense. Okay? So now here's the thing. What if I want to be 99% confident? Well, I know by the empirical rule, I can be 95% confident, let's say, between 2 standard deviations using the empirical rule. But what if I want a 99% confidence? What if I want to be 80% confident? Well, it's not going to be 2 anymore. It's going to be something else, right? And we have to figure that out. Well, that's where Z-scores come in. Okay? Because remember what Z-scores tell us. Z-scores tell us how many standard deviations above and or below the mean a particular value comes up. So instead of using 2 here, we're going to replace this 2 with a Z-score, right? So here the Z-score is 2. But what if we use a different percentage? What if we want to capture 99% of all the values? What if we only want to capture 93% of all the values? What if we want to capture 98? So based on that percentage, it's going to change our Z-score. It's going to change how far we need to go out, right? So that's where we're now going to replace this with a Z-score. And that's going to help us determine the second piece of the confidence interval. So let's talk about that. So the second piece is the margin of error, which is going to be Z alpha divided by 2 times sigma over the square root of n. And there is our final piece. Okay? So the 2 pieces of the confidence interval for the population mean is going to be the point estimate x bar plus or minus the margin of error, which is the Z-score, Z alpha divided by 2 times sigma divided by the square root of n. Okay, so now now let's talk about a little bit more specifically how it works. Okay. So that's the idea, and that's how we come up with this formula. But let's now use this, okay, and show you how we get the z-score. So we use the idea of a 95% confidence interval and the empirical rule to come up with the two standard deviations. But again, that's just a general rule. Let's now talk about, well, what about other situations? Okay, so here's how it works. Let's say it says find the point estimate for the population mean mu for a 90% confidence interval. Assume that the distribution is normally distributed with a population standard deviation of 6 minutes. A random sample of 28 pizzas, or excuse me, a random sample of 28 pizza delivery restaurants is taken and has a sample mean delivery time of 36 minutes. Okay, so in this case here, the point estimate is x bar. And what is x bar? Well, it says that of the sample 28 pizza delivery restaurants is taken. The mean delivery time for those 28 pizza delivery restaurants is 36 minutes. So that means x bar is 36 minutes. Okay? So x bar is 36 minutes. Okay? They also tell us that the standard deviation for delivery times, for all delivery times, is 6 minutes. So sigma is 6 minutes. Okay? Now, let's see here. And n is 28, right? So sample size is 28. And so what they want to do is let's construct a 90% confidence interval for mu, the true average time it takes to deliver pizzas. Okay? So now here's the thing. Let's now, before I do this problem, now I'm going to teach you some other terminology. So what we call this is the confidence level. Okay? The confidence level always represents the middle area, the middle percentage of data, right? Think of what we did with the empirical rule. It was the middle area, okay? The confidence level always tells you the percentage of values that fall between the two, the middle, that fall in the middle, okay? As far as how far we want to go out, okay? Now, in this case here, the confidence level is 90%. So that means the middle area here is 0.9, okay? So now, if 90% is in the middle, what percentage is outside the middle? Or, in other words, in the tails of the graph. So here and here together. So if 90% is in the middle, how much is left over? Well, 10%, because the whole thing has to add up to 100%, right? The complement rule. So if 90% is here, that means 10% have to be in the tails. And here's where I'm going to define alpha. Okay? So remember, the confidence interval for mu in general is x bar plus or minus z alpha divided by 2 times sigma over the square root of n. So I'm going to explain alpha. What is that alpha? Okay? Alpha is the area in the tails. That's all you have to know. It's the area in the tails. So technically, what we're going to do is we're going to define alpha as 1 minus the confidence level. So in this case here, it's going to be 1 minus 0.9, which equals 0.10. So in this case, alpha is 0.1, which is, in other words, the area in the tails. Alpha is the area in the tails. That's all you have to remember. That's alpha. Okay? So in this case here, alpha is in the tails, but because it's a normal distribution, how do we know it's a normal distribution? We'll get to that in a second. But because it's a normal distribution, we know half of alpha is this tail, half of alpha is in this tail because it's symmetric. Remember, normal distributions are symmetric, right? So we know that this is alpha over 2, which is equal to 0.05. And we know that this is alpha over 2, which is also equal to 0.05. And we're done. So now, the critical value is this right here. It's the Z-score on the standard normal distribution that captures 90% of all the Z-scores. Okay? Why? Because we know if X bar is normally distributed, right? If it's normally distributed, we can transform any normal distribution into the standard normal curve. That's why we can use a Z-score here, okay? And it doesn't matter what situation we're using. As long as X bar is normally distributed, then we're good. Now here's the thing. Is X bar normally distributed? Yes. For 2 reasons. Do they tell us? Hold on. No. Yes. They say assume the distribution is normally distributed for the population. So the population gives it to us. So X bar, or X, is normally distributed, right? With a particular mean and standard deviation. But realize that the central limit theorem also gives it to us because n, oh no, I'm sorry, it doesn't give it to us. And so in this case here, the central limit theorem does not help us because n is not greater than 30. So that means the central limit theorem is not available to us. But that's okay. They tell us the population is normal. So we know what? X bar has to be normally distributed with a mean of mu, which we don't know, and a standard deviation of sigma divided by the square root of n, which in this case is going to be 6 divided by what? The square root of 28. Okay? And so that's that's what we start with. So this is the important piece. This is what we need to know. Okay? So we know this now. That's what we're going to use. Okay? So now let's get back to this. So this is what we need to know to even get to this part, right? We can't construct a confidence interval unless we know X bar is normally distributed. So just keep that in mind. So now, back to this. We still need to know our Z-score for this piece. Well, now, all we have to do is we can use either the Z-table or our calculator, right? So in order to use the calculator or the table, we need to know the area to the left of our critical value. Well, what's the area to the left? Well, remember, the middle from here to here is 0.9. We have to also add this tail here, which is 0.05. So we have to add 0.9 plus 0.05, so the area to the left is 0.95. That's the area we need. Don't forget that, okay? Because if you end up putting in the wrong number, like 0.9, I have students that will do that from time to time, you'll get the wrong Z-score and then your interval is incorrect, okay? So now, this is what we're going to use. Now, to find z, okay, so now z alpha divided by 2. Now, why is this called alpha divided by 2? Very simple. It's the area to the right of the critical value. What's the area to the right? Alpha divided by 2. That's why we call it that, okay? So z alpha divided by 2 is equal to inverse norm, right? Inverse norm is what gives us values for a normal, right? So it gives us x values or z-scores as long as we put in the right mean and standard deviation. So now, for this z-score, what's the area to the left? 0.95. And then after that is the mean. Well, what's the mean for the z distribution? 0. Remember, standard normal. And the standard deviation for the z distribution is 1. And so this will give us what? It'll give us 1.96 if you put it in your calculator. And there's your z-score. So now we have what we need. So this goes right in there. Now, do we have everything we need? Yes, because we've got the z-score now. X bar we have as 36. We got that. Sigma we got as 6. Got that. N is 28. Got that. So how do we calculate this? Well, we just plug and chug now. So it's going to be 36 plus or minus z alpha divided by 2, which is 1.96, times sigma divided by the square root of n, which is right here. So 6 divided by the square root of 28. And so now all we have to do is plug and chug, right? So with the margin of error, let's calculate that. So the margin of error here is going to be 2.22. So 2.22, so it's 36 plus or minus 2.22. So our final answer is going to be this plus or minus this. So what do we end up with? We end up with 33.78. And then we also end up with 38.22. And that is our confidence interval, okay? So if we wanted to go to the significant digits, we would, as far as accuracy, you would only have to go out one decimal place, but that's fine. So this is your confidence interval, okay? And now, we'll talk about interpreting this a little later, but, well, actually we can talk about it now, that's fine. So if we talk about interpretation, but before we do that, let me also show you the function on your calculator that can do this. So I wanted to show you the way you plug and chug in the formula. So again, you can use the inverse norm function on your calculator to get your critical value. Okay. Also the z-table. You can use your z-table to do that, but calculator is much easier. But there is a function on your calculator that will give you your confidence interval without having to do any of this. Okay. So, but again, I wanted to show you this because I want you to understand what's going on, the concepts behind constructing this confidence interval. Okay. So now, that you know what the confidence level means and what alpha is, now what we can do is talk about using this formula or using this function on your calculator. So the calculator has a function under your under tests. So you go to stat on your press stat on your calculator, and then you're going to use the menu tests. So now you're using the third menu. So you have the edit menu, the calc menu, and now the test menu. So under tests, you'll find this function, z interval. and I believe it's number 7 on the menu, okay? So this is the function you will use to construct a confidence interval for mu, okay? If sigma is known, okay? This is all under the assumption that we know sigma, okay? So we'll talk about what if sigma is unknown later on, but for the time being, Z interval is based on a normal distribution when sigma is known, okay? And in this case, it is known. So keep that in mind. So now, how does the Z interval work? Well, the Z interval gives you an option. So the first option is you have to pick what you're inputting. Are you inputting statistics or are you inputting data into the function? So you have to choose data or stats. So in this case here, we're not putting data in there, we're using statistics. So we would choose stats. And then under this menu for stats, it's going to ask you for sigma. It's going to ask you for X bar. It's going to ask you for N. And it's going to ask you for the confidence level. So all you have to do is plug that information in. And guess what? That's what the problem gave us. So at the very beginning, the problem gave us X bar, sigma, N, and the confidence level. So all you have to do is just plug it into the calculator, hit calculate, and you're done. So you just plug in sigma, which is 6, X bar, 36, N is 28, and the confidence level, it's a 90% confidence level, so you want to put in 0.9 into the calculator. So CL is 0.9. And then what this is going to give you is the same interval. Okay? So just be aware of how to use the interval function. We're going to do more examples next time. So this is just an introduction to confidence intervals, how they work, how do we develop, and this is specifically just dealing with for the mean right now. So once we get a handle on how to apply this to different problems, we're going to start talking, and again, we're going to start with the assumption that we know the population standard deviation sigma. So once we do a few examples of that, then we'll say, okay, what about other things that we can do? And then we'll talk about, hey, what if we don't know sigma? Okay, but that'll be for next time. Other than that, I hope you had a great time. I hope this was very helpful to you, and have a great day. Okay, welcome back. And so today we're going to continue with Chapter 8 on confidence intervals. And so we're going to do some more examples involving problems where we know the population mean, or excuse me, the population standard deviation, and we're looking for a confidence interval for the population mean, mu. Okay, so let's get started. So let me get my marker here. Actually, let me grab another one. Sorry about that. Over here. Okay, so here's first example. This is dead, of course. Okay, so here's the first one. It says, suppose scores on exams and statistics are normally distributed with an unknown population mean and a population standard deviation of 3 points. A random sample of 36 scores is taken and gives a sample mean of 68. Find the confidence interval estimate for the population mean exam score. Well, so the population estimate, right? So the population mean estimate would be X bar, the sample mean. Well, what's the sample mean for these 36 scores? Well, it's going to be 68, right? So they tell us 68 is the sample mean. N, the sample size is 36. The 36 test scores. The standard deviation, sigma, they tell us is 3 points. And they want a 90% confidence interval. So they want a confidence level, 90% confidence, so the confidence level is 0.9, right? 90%, 0.9. The middle area is 0.9. So they want a 90% confidence interval for mu. What is mu? Mu in this case is the true average score for all students taking this test. Okay? So let's say that again. This is the average score for all students taking this statistics test. Okay? So now, again, the formula is X bar plus or minus Z alpha divided by 2 times sigma over the square root of n. And we can get this value here if we know the distribution of X bar. In fact, we can't go any further unless we know the distribution of X bar, which we do, because this is bigger than 30. So n, the sample size is bigger than or equal to 30, which tells us by the central limit theorem that X bar is approximately normal with a mean of mu, which we don't know, and a standard deviation of X bar of sigma divided by the square root of n. Okay, which we do know. So we know that this is 3 divided by the square root of 36. Okay. So now we can figure out what the z-score is because we know it's normally distributed. So we can talk about z-scores. And we can get this z-score by using inverse norm. And if you plug in inverse norm, you have to know the area to the left, right? So what's the area to the left? Well, let's figure it out. Well, here's my picture. The middle area is what? The middle area is 0.9. What's the area in the tails? What's alpha? Remember, alpha is 1 minus the confidence level. Or, in other words, the area in the tails. So 1 minus 0.9 equals 0.10. So we know that the alpha is equal to 0.1. The area in the tails is equal to 0.1. And so, again, since we know it's normal, then it's going to be symmetric, right? Z-scores are symmetric. We need this z-score. And so what we need is the area to the left of this z-score. Well, if alpha is 0.1, then we know that half of alpha goes here, which is 0.05. And of course, half of alpha goes here, which is 0.05. So now the area to the left is 0.9 plus the 0.05. So just like before, it's 0.95. So the area to the left that we're going to put in here is 0.95, followed by the mean of the z-scores, which is 0, right? Standard normal has a mean of 0 and a standard deviation of 1. And so now, like we did before, the critical value is 1.96. And of course, some of these you're going to know. We're going to do so many of these that you're going to just know that when we do a 95, when we do, oh, hold on, that's not at 1.96. That's 1.645. I made a mistake. I was focusing on this, and you're going to get the wrong answer. So remember, this is the area to the left. It's a 1.645. So if you put that in there, it's a 1.645. I was thinking 95% confidence, so I apologize for that. So for a 90% confidence interval, you're going to get 1.645. So I believe on the last video, I made a mistake of doing 1.96. No, I didn't. No, I might have. I think I might have. I don't know. I'll have to go check. But anyway, we know now, right? Okay. So it's 1.645 is the critical value, not 1.96. Okay. So what do we do with that now? Well, now we're going to put it into our formula. So now we know the pieces. So it's going to be 68 plus or minus 1.645 times sigma divided by the square root of n, which is 3 divided by the square root of 36. And so we get 68 plus or minus what? Oh, and I think I did use the wrong number last minute. 1.645 times 3 divided by square root of 36, which is 6. And we get 0.8225, which we're just going to go 0.82. And so that is the margin of error. Here's our point estimate. So what does that give us? That gives us, well, 67.18 to 68.82. And let's see if we did it right. That is correct. So this is our confidence interval. Okay. So the other thing too is we can do this using the formula, but it's easier if we use the function. So if we use the function on our calculator, then what we could do is just plug in the information to our calculator. Okay. So what we can do is we can use Z interval. Why? Because we know sigma, and we're talking about a confidence interval from mu. So it's going to be Z interval. And the first part is we're going to be using data, or excuse me, not data, stats. They're giving us statistics. So this is the pieces of information right here. So all of this is going to go in the Z interval. The only thing we have to choose is make sure we choose stat for our input. And then that's going to give us the same information. It'll give us 67.18 and 68.82, which is the same thing that we got before. Now the calculator gives you 3 decimal places. Again, you don't need to. Make sure you just round to the appropriate number of decimal places. Here, 1 would actually have been sufficient, but that's fine. It doesn't matter in this case. Now, interpretation. Here's where the interpretation comes in, and you need to make sure you understand the correct interpretation. And there's really 2 correct interpretations for a confidence interval. One is more used than the other. But there are many different ways that I get from students, many creative ways, creative interpretations that students will give me that are wrong. Okay? So the way you interpret is you have to make sure you include three important pieces of the confidence interval. You have to mention the confidence level. The interpretation has to be about the parameter of interest, and you also have to mention the interval. Okay, so you have to do that. So in this case here, the way we would interpret this interval is that we can be 90% confident. Okay, I want you to write this down. I'm going to write it down in a minute, but I want you to write this down. We can be 90% confident that the true average score for all students taking this test is going to be somewhere between 67.18 and 68.82. That's the interpretation of confidence interval. Okay, so let me write that down. Okay, so we can be 90% confident the average score for all students taking this exam is somewhere between 67.18 and 68.82. And everything I underlined are the important pieces you need to have. Okay? So we need a confidence level, C. We need to up the parameter of interest, P, and we need the interval, right? It has to include the interval, right? The two numbers, right? So always remember CIP. We need a confidence level, we need the interval, and we need the parameter of interest. This is going to be important, okay? So as long as you have these three things in here, which this template, so I would memorize or practice using this template. So we can be blank % confident that the parameter of interest is somewhere between this and this. And that's what you have to do. That's the correct interpretation. The other interpretation is from a sampling point of view. This would say that, hey, if I took 100 samples of the same size, so in this case, what was the sample size? 36. So if we took 100 samples of the same size, of size 36, and we calculated the sample mean, or excuse me, I'm sorry. Let me start over. If we take 100 samples of the same size, size 36, and we construct a 90% confidence interval for mu for all 100 samples, so for each of the 100 samples, we construct a 90% confidence interval for mu, that we would expect that 90 out of the 100 confidence intervals will contain the true mean. Okay? That's the other interpretation. Also correct, they're equivalent interpretations. They mean the exact same thing. This one is more common. Okay? Easier to understand. Okay? Okay, so now let's do the next one. So now it says here, suppose average pizza delivery times are normally distributed with an unknown population mean and a population standard deviation of 66. Oh, we did this one already. We did this one already. Never mind. Let me do another one. I don't want to redo that one. We did it last time. Oh, here we go. The specific absorption rate, SAR, for a cell phone measures the amount of radio frequency energy absorbed by the user's body when using the handset. Every cell phone emits RF energy, radio frequency energy. Different phone models have different SAR rate measures, which is the specific absorption rate, SAR. So different phone models have different SAR measures. To receive certification from the Federal Communications Commission, FCC, for sale in the United States, the SAR level for a cell phone must be no more than 1.6 watts per kilogram. So they give us a table here, okay? So here they give us a table of data for the SAR rates for all different models of phone. And so in here there are, how many cell phone models do we have? 1, 2, 30. Yeah, there are 30 models. Yeah, there are 30 models. 1, 2, 3, 4, 5, 6. Yeah, 30 models. Wow, this is pretty old. What year is this? Yeah, there's a BlackBerry Pearl. Oh, the iPhone 4S. The Samsung Nexus. Yeah, I don't see any. Yeah, this is, I think, pretty old. Anyway, so we've got these 30 models, and they give the data. Okay, so for this one here, I'm just going to write out the data. We don't need to know the cell phone models, but here's the data. So here's all the SARs, okay, for the 30 models, okay? So I'm just going to write them out. Okay, so here's the data. So the first thing we're going to do is, what do we know about this problem? Well, we know that, let's see here. no, that's all they give us. So here's what we need. It says find the 98% confidence interval for the true population mean of the specific absorption rates for cell phones. So we want, that's mu. So for mu, which is the true average absorption rates for all the models, okay? And they also tell us sigma. So sigma here, they tell us is 0.337. So here's what we're going to do. Again, we could do this two different ways. We could use the formula, or we could use the function on the calculator. So first thing is, either way, we have to put the data in the calculator because all they give us is data. Okay, so this is going to be an example. When we use the function, we're going to use the data option because this is all they give us. Okay, so we're going to enter the absorption rates. So let's do that. So I'm going to go to stat edit, and I'm going to pick one of my lists, and I'm going to plug in all of these numbers. So you do the same thing while I'm doing it. Okay, so I got all 30 numbers in there. So I've got it in my list one. So the first thing I'm going to write down is, okay, I've got my data in the list one. Okay, so now I'm going to erase this because I'm assuming that you guys already have it in your data. If not, pause it and then finish, and then continue on with this. So here's the information again. So sigma, so n equals 30, sigma equals 0.337. And so list one is where I put the data. Okay, and we want a 98% confidence interval for mu, where mu is the true average what? Absorption rates, specific absorption rates for cell phones, for all cell phones, or for all the models. So now we can use this formula, right, because we know sigma, so it's going to be x bar plus or minus z alpha divided by 2 over sigma over the square root of n. And we do know that x bar is normally distributed. Why? Because n is 30. So they don't tell us about the distribution of the absorption rates. So we can use the central limit theorem, though, to say that x bar is approximately normal, so it's going to have a mean of mu, which we don't know, and the standard deviation is going to be sigma over the square root of n. Okay, so now we can use this. So now, what is the z alpha divided by 2? Well, what is that? Well, it's a 98% confidence interval. So again, if we draw out our picture, right, we know the middle has to be 98%, 0.98. So that means alpha is equal to what? 0.02. So then half of alpha goes here, so that's 0.01. Half of alpha goes here, 0.01. So now my z alpha divided by 2 is this critical value, so the area to the left is what? 0.98 plus 0.01, 0.99. And so if you use the table or use inverse norm, z alpha over 2, right? You're going to put in 0.99, comma 0, comma 1, and that's going to give you 2.33 for your for your critical value. And then you just plug and chug. Now the only thing we don't know is x bar, but what can we use to find x bar? We can use the data in L1, and we can get x bar by using 1 var stats on your calculator, and then x bar we can get as part of the output. So now I'm going to go to stat calc now, and I'm going to put in L1 for my function, or into my function, and x bar is 1.02. 1.02. Do I want to go out to, yeah, let's go out to 3 decimal places. So 1.024. 1.024. 1.024. Okay, so now I've got my x bar, right? So now, do I have the pieces? Yes. I've got x bar, I've got sigma, I've got n, and I've got my z alpha. So now I can just plug and chug. And so my confidence interval is 1.024 plus or minus 2.33 times 0.337 divided by the square root of 30. And so this is going to equal 1.024 plus or minus what? Point 143. 0.143. And so now what do I get? Well, my left endpoint is going to be what? 0.881. And my left endpoint is going to be 1.167. And I'm done. So the interpretation, how do we interpret this? We can be, where is it? We can be 98% confident, right? That the true average, what? Average absorption rates for all models of cell phones will be somewhere between 0.881 kilowatts per, is it watts per kilogram. So between 0.881 watts per kilogram to 1.167 watts per kilogram. Okay? And that's it. So I hope that made sense. If not, just review this, pause, review, make sure you understand the way these work. Okay, so now the formula, right? So now we can also use the formula, right? So let's see how this works. Not the formula, but the function, right? So remember the function, we don't need 1 var stats because all we have is the data, this and this, right? So if we have the data, then we have everything. We got this, right? This is the confidence level. So I can use Z interval, and we're going to use data this time, right? You just plug in the data, right? And then you're going to use sigma, right? Sigma, you have to put in sigma. And then you're also going to put in the data X, right? Where's your list? Your list, right? It's going to ask you for a list, and you're going to put in L1 or wherever you put your list. And then after that, it's going to be the confidence level. So confidence level here is 0.98. So you just put the confidence level 0.98. And then you calculate, and what do you get? You are going to get, let's check here. .88087 and 1.1671, which is pretty much spot on of what we got. Okay, because if you round this, you get 0.881 and 1.167. So you get the same thing. Okay, so it doesn't matter which one you do, you get the same answer. So just make sure that you understand what's going on, whether you use a formula or whether you use the function on your calculator. Okay. Let's see here. Let's see what we got. We got. Okay, so what if we change the original problem for the statistics test? What if instead of a 90% confidence interval, we want a 95% confidence interval? So all we'd have to do is just go back to the calculator and change what? We're just going to change the confidence level, right, if we're using the function. Or just change the Z-score. The only thing that will change is the critical value, Z alpha divided by 2. So that one I would suggest doing so that you can see the difference. So if we do that one, and I'm just going to use the calculator. So this is the statistics problem again, where we had X bar equal to 68, standard deviation was 3, N was 36, and we had a confidence level of 90 before. Now we're going to do a confidence level of 95%. Okay? And so if we use this information and we use Z interval, okay, so this is the statistics test, right? Okay, so the only difference is we're doing a 95% confidence interval. And so if we do that, we get this. We get 67.02 and 68.98. Okay, so that's what we get for a 95% confidence interval using the calculator. Now, the margin of error for both of these. Okay, so let's look at the original, the other one. The other one, where is it? So this is a 90, this is the 95% confidence interval. Let's do this. So 95, yeah, let's do this one. So 95% confidence interval for mu, we found was 67.02 and 68.98. For the 90% confidence interval, we found this. We found that it was 67.18 and 68.82. Okay, so recall this was from the previous, the original problem. Okay, so we went from a 90% confidence interval to a 95% confidence interval, and everything else stayed the same. So what happened to our confidence interval? So notice something here that for this endpoint here, it went down, right? So this decreased, so going from 90 to 95, this decreased, but this side increased. So basically, this side went that way, this side went that way. So what happened? The confidence interval got wider, right? So if we increase the confidence level, it increases the confidence interval. Okay, so why does that happen? Well, it should be intuitive based on the anatomy of a confidence interval, right? You got two pieces. You got the point estimate. That doesn't change, right? The only thing that changes then, it has to be the margin of error, which you should know that because what do we talk about? The confidence level affects? It affects the Z-score, the critical value, which is what? Part of the margin of error calculation. So let's look at that. So if we look at the distribution here, so here's our Z alpha divided by 2, right? Here's our confidence level, right? What happens if the confidence level increases? Well, the middle area is what? Increasing or decreasing? Well, it's increasing, right? So that means if the middle is increasing, what's happening to the boundaries here, these cutoffs? Well, they're moving away, right? So the critical value is moving that way, which is increasing, right? So if the critical level increases, then that's going to push our Z-score to go up. Well, what's the margin of error calculation? Well, margin of error, remember, is Z alpha divided by 2 times sigma divided by the square root of n. Well, sigma doesn't change, that's fixed, right? And we're assuming the same sample size in both cases. So the only thing that's changing is this. So if this goes up, what happens to our margin of error? Well, the whole thing goes up, right? You multiply by a bigger number, you get a bigger result, a bigger product, right? So that's why as you increase confidence, you increase the confidence interval. So basically, if you want to be more confident about whether you have the true parameter, right, the true population mean, then you need to have a bigger net, right? You have to have a bigger confidence interval, okay? So keep that in mind. So that's the relationship between increasing confidence levels and what happens to the confidence interval. It goes up, it increases, so it becomes wider. Okay. Let's see here. Let's see here. Okay. Okay, so what we'll do is we'll leave there, and next time what we're going to do is we're going to talk more about the margin of error, and we'll start talking about, hey, what happens when we play around with the sample size, and then we'll talk about things like minimum sample size and finish this out for confidence intervals for the mean, and then what we'll do is we'll talk about what happens if we don't know sigma, because next time what we'll do is we'll get to the point where we say, okay, well, what if we don't know sigma? What do we do then? Do we just pack up our bags and go home? No. We're going to introduce something new. Okay, thank you and have a good night.